Okay, so in this short video we're going to talk about thermocouple positioning on your mould. Okay, there are a number of different places where you can put the thermocouples on your mould, and all will have advantages and some will have disadvantages. Depending on the situation that you've got, we need to determine where is the best place to put that thermocouple in your mould. So we'll start, there's a bit of a scale here, so we'll start, if you were doing R&D, for example, and you just wanted to measure the inner air temperature of your mould, quickly, dip in, measure the temperature, and get back to production. So let's put our mould here. Let's say our mould is here, and we've got a slip ring, and with an arm coming out here. So where is the best place to measure the temperature of the inner air? Well, the easiest thing to do is just to put a simple thermocouple through the vent pipe, measure the temperature that way, bring this round and plug it in to the slip ring. That's easy to do. If you're doing R&D, then you can use some of the BearBeated thermocouples. Okay, so a BearBeated thermocouple has got a very high response to changes in temperature, and so that will let you see all the intricacies of what's happening inside that mould. Okay, fast response, because the part of the thermocouple that is doing the business is not in any way sheathed to reduce the speed at which the temperature can get to that thermocouple probe. And if you're operating in a production environment and you've got your guys demoulding this every time, now let's say the flange is here, well, they're going to have to remove that thermocouple every time. So then we want to move away from just the simple cable with a BearBeat thermocouple. We want to get into something a little bit more robust. So what we could do is use the production probes that we've got. And the production probe basically puts a conduit around the probe, and then at the end of the probe there is a sheathed tip, okay, to protect that bead from powder, okay, and melted powder. So for example, if you use just the BearBeated thermocouple and you finish and you take that out of the vent pipe, you'll find that the BearBeat is probably covered in a little bit of plastic now. And what you can do is you can either just cut that off, twist the ends together and make a new thermocouple, or you can put a torch, a flame below that, and burn the polyethylene off. It gets the polyethylene off, it also destroys some of the sheathing near the tip. Okay. Excuse me. The best way to do it is, of course, have this situated in a position where, as the powder is tumbling, the bead is not actually in that powder pool. So we've moved to the production side. We've got one production probe coming up. We could have a bracket here, or a clamp, like that's such a badly drawn clamp, but hopefully you understand what I mean. And like an earth clamp that a welder would use, and clamp the probe, which would be stopping here, coming down into the air. Clamp that probe to maybe a post or something beside the vent pipe. Okay. You could consider perhaps just having an extension cable coming up here. So we could come out of here, we could come up to the side and have another socket on the top, and then you could plug the short thermocouple in there. So when it was time for demoulding, the operator would just unplug this. The probe would remain part of the vent pipe, and the probe and the vent pipe and even the lid would come away in one go, and you're left with this extension attached onto the side of the framework. Okay, what else could we, the next stage that we can go to? Well, inner air is absolutely the best method of getting processing information back from temperature moulding, okay? That's the one that all the research has been done about. That's the one that will tell you when to drop your second shot of material. That's the one that will tell you when the peak internal air temperature is right, when you've got your optimum internal air conditions. That's the one we want at all, if at all possible, okay? But that's not always the easiest one to put in, because you're dealing with vent pipes, you're dealing with probes going into the vent pipes, you're dealing with operators touching that, okay? So what some of our customers do is they say, well, look, we are using a single wall part, okay? Just single wall, polyethylene, pretty straightforward. We still want to measure the temperature because we're looking for consistent quality, we're looking for traceability. If our customer says, how was this one cooked, we can go into our server and find out. But we don't want our operators touching those probes. So what some of our customers do is they simply take the probe decay control and they put it into the bottom of the mould. Okay. They don't put it into the air, they just put it into the bottom of the mould. They're measuring tool temperature. Well, not quite tool temperature, they're measuring an interface temperature. Let me show you where they put that probe. So if I draw this blue, the blue wall of the mould, the metal mould wall, and then we use red to signify what the plastic would be doing. So there's a plastic wall there. Okay, and that probe would come in, and it would be there would be a hole drilled in the mould wall, and if it's aluminium, you maybe thread that, and then the cable that comes from here would have a bolt on the end of it. Okay, bolt on the end of it. Cable goes out to the K control slip ring, and the actual tip of the thermocouple is just embedded here. Okay, so you can see that it's just touching the interface between the mould wall and the plastic. Okay, it's not going to give you that beautiful internal air temperature curve that you get. You know, it's showing you the peak optimum temperature to take it to. It's just going to show you a temperature. It's going to rise up. But the first time you do this, the first time you run this, you put two thermocouples, one to measure the internal air inside the part here, internal air here, and you use one to measure the mould wall temperature here, and you correlate them, and you say, okay, for a perfect part, we need to take it out of the oven here, okay, and it will rise up. So what temperature at that point in time is the mould wall temperature? Well, you just go up and you say, okay, so there's the temperature there, T wall and the T internal mould air. Okay, so there's a correlation, if you like, between the mould wall temperature and the inner air temperature. If you're doing single layer parts, that gets you a good way towards removing variability to do with ambient temperature changes. If it's a very sensitive material, if you're into, excuse me, if you're into the nylons and the engineering materials, the exotic materials, you don't want to do that. You want to measure the inside air temperature. But for regular PE, this takes you a long way towards consistent control, compensating for variations in ambient temperature. If you are multi-layer, second, 2-layer, 3-layer, 4-layer, that's not going to work for you. You're going to need internal air temperature measurement. Okay, so you need therefore to get a probe inside there. So the two ways we can do that let's just work over here. The two ways we can do that, if we've got our mould here, yeah, we can either go in the top through the vent pipe, okay, or we can come in the side via some kind of part of the tank that's going to be cut out. So if it's a tank, you're probably going to have an outlet here to screw or attach the pipe work for the system that the tank's going to be installed into. So that's going to be cut out. So therefore we could put a probe in here. Okay. So we're measuring internal air here, or we're measuring it here. Okay. Now again, this temperature is close to the walls, close to the corner of the mould. It's not in the centre. And I would say just at this moment in time that this internal air temperature trace is good to compare cycles. It's good to compare different cycle times, but it always, for proper comparison, it needs to be the average temperature of the inner air. Okay, so if you go way down to the corner here, then you've got yourself something which perhaps is it's not always going to be the same. So if you measure the temperature here in this tank and measure the temperature here in another tank, you cannot compare them. Okay, so I would even say it's worthwhile correlating this temperature with this temperature. Okay, disadvantages with doing it this way when you're for multi-layer stuff is, well, you probably need that vent pipe to get your second, your third shot in. Thermocouples are going to get in the way. And when it comes to demoulding, again, we're back to this scenario here. If you remember earlier, where the operator has to take the thermocouple out, you've got this floppy lead, okay, which is increasing the chances of it breaking. So what I would say is, find a spot whereby you're going to drill a hole in it anyway, get a probe in there, excuse me, and what you can do is build a jig, as I'm sure you will have already thought about. Build a jig to easily remove that probe. That jig could be based on an over-center clamp. As you pull the clamp back, the probe comes out with it. It could be based on a spring, so you just pull it out and lock it in position. Then the guys can demold. You've got to remember to put it back in. Okay. It's always useful to prevent the guys from opening the lid, lifting it up, and basically forgetting to disengage the thermocouple and wrecking the connection to the K control. It can be a useful thing to put a small piece of chain between a fixed point in the thermocouple and the base of the mould. So if they are lifting it up with the crane, it'll catch in the excuse me, it'll catch in the chain and stop, so they can disengage the chain and then be reminded to remove the probe. Excuse me. So the actual probes themselves, we've got a couple of different types that we have used over the years. One of the we're looking for a bit of a balance here. The fastest response, the best data that you can get back from a probe is found when it's just a bare bead, okay? A bare single point bead. We'll call that BB, bare beads. Bare beads give very fast reaction times. Okay, so if you're doing some kind of R&D work or some kind of process setup or product setup work, you probably want to start with a bare bead, because that will at least let you know what's happening inside that mould. Okay, that's going to help you understand what the powder's doing. Okay, but that's going to be useless for production. Your operators are going to have that wrecked in no time at all. So I see these bare bead probes as almost disposable. You use them once or twice and you get rid of them. We can supply a roll of that cable, okay, and then you can make your room up very simply. Roll of cable and a dozen plugs to go into the K control in your you're good for that kind of R&D work. So we're looking for something a bit more robust. So let's go to the opposite end of this. Okay, so what we're talking about here is a sheathed production probe, much like you would see if you've got an extruder. You know, you see that those process probes, or an oven, you see a big process probe coming in the top. So what we've got here, we'll call this a sheathed, okay, TC, and basically that is a BearBeat, yeah, with a sheath around it, and that sheath, as an absolute maximum, we're talking 6 mil. Okay, we're talking 6 mil maximum. Even 6 mil is absolutely on the limit in terms of the speed of the reaction. So we're going to put down, for a 6 mil probe, we're going to put down slow reaction. Okay, so if you were to put 2 probes into the K control, a BearBeat and a 6 mil production probe, and you were to measure them at the same time, we're going to get the BearBeat is going to come up nice and fast and down. The 6 mil one is going to be slow to react, so it might do something like this. Okay, so it will be slower to react, slower to respond, really robust, really strong, harder to break, but doesn't really give you the information in a timely fashion. You can correlate it, as we talked about up here, and say, yeah, that's okay, we'll work with 6 mil, we'll get up here, and when it's finally responded, we know that the true temperature is back here somewhere, and adjust for that. But I guess what that is, it's just slowing things down. It's not giving you the true reading. It's giving you consistency, but perhaps not precise real temperatures. There's 2 in between here we're going to now talk about. The 2 in between is to use a sheathed thermocouple, which is 3 mil in diameter. The 3 mil in diameter probes are much more fast reacting. Okay, so if you were to do a 3 mil probe against that red one, we're probably, 5 degrees out here and there in terms of the response. So it's not a big deal. Our cycles are long, 20-minute cycles, 30-minute, 40-minute cycles. So we're not looking for fast lightning response here. 3 mil is spot on. Problem with 3 mil is if you want a long 3 mil probe, say going into the vent pipe, it's maybe going to be 300-400 mil long, and before very long there's a good chance that the operators will have bent those probes and damaged those probes. The optimum one that we're using now is the 6 mil probe on the body, okay, with a reduction to 3 mil at the point where it matters. Okay, so let me just get a bit of space here, up here. Oh, it's a mess. And with the 6 down to the 3 mil probe, that there is the safest in terms of accuracy and in terms of robustness as well. So it looks something like this. You've got a 6 mil probe, and then for the last 50 mil or so, you've got 3 mil diameter. So you have a 3 mil diameter at this point here, and then you have the 6 mil diameter for this length here. Back here we've got our convoluted tubing to show that working. Okay, 6 mil is good because we can secure fittings to that as well, which is very useful. Now we're going to take a slight detour. I want to talk about static in rotational moulding and how that affects our system. Okay, so whenever you take a mould out of the a part out of the mould, I'm sure you will have heard whereby as the mould comes out, the static charge is built up, and if you touch that, you get a bit of a dig. There's about 20,000 volts generated there on removing that. And that's all that's all building up just when you take it out. Okay. If the mould itself is well earthed, then that should just dissipate out of the mould. But often with the grease and whatnot around the bearings, that charge is not dissipated to earth via the mould. So what happens? It's dissipated to earth whenever a guy touches it, bang, or through the thermocouples. And that has been a problem in the past with BearBeated thermocouples on the electronics. So you should always disconnect your probe if you're using a BearBeat thermocouple. Disconnect it before demoulding. Okay, otherwise you'll be sending 20,000 volts down a thermocouple cable to your radio at the back of the arm. We have got some very robust protection on there, but why do it if you can avoid it? Okay, so with that in mind, we therefore say that when we move to sheathed thermocouples, they should not be earthed thermocouples. Okay, so that means if you look here, this one here, you see that the thermocouple BearBeat is inside a sheath. Well, our thermocouples that we supply, the sheath is packed with with an insulating and non-conductive. One second, John, could you bring me up a production probe, please, just for a K-control production probe, just to show on the video here that I'm recording.